All right. So in this exercise, we're going to be looking at the string reversal property, and we're going to be trying to um, prove something about string reversal. So firstly, just a like high level intuitive definition of string reversal. So what does it mean to reverse a string? The definition is really just in the name. So if I have a string like 0, 1, 1, and I want to take its reversal, denoted with this lovely symbol R here, then what I do is I take the last symbol of the string and place it at the beginning. So I get 1, then second to last, and I place it in the second position, and so on, right? So then the string reversal of 0, 1, 1 is 1, 0, 0, right? So intuitively, it's just really that's what it is you instead of reading the string from left to right, it's as if you were reading it from right to left. Now, a more formal definition of string reversal can be given sort of recursively. Okay. So we define reversal by saying how it would work on smaller parts of a string. So for instance, the way that we do this for string reversal is we have basically a single base case where the base case is for the simplest possible string. And so in this case, the simplest possible string is the empty string. And if you want to reverse the empty string, right? Well, it's as if you had something that had no symbols in it, right? So then reversing the empty string just gives you the empty string again, right? So you can just imagine it if you know Python, if you had like an empty string like this, so this was like assigned to S, then if you did the string reversal sort of with a Python program, then it would also return this string, right? Is the base case. And then we have the sort of recursive case, right? So the recursive case is, well, if you have a string, some string, then what we're going to do is we're going to sort of reverse it symbol by symbol. So to define this in terms of the recursive case is, well, if I have a string in sigma star and I have a single symbol from sigma, then the reverse of W sigma is, well, you take this sort of final symbol, the symbol at the end, and you place it at the beginning, right? And then you let the recursion handle the rest of the string reversal. So then you do W reverse, right? So the way that this would work on this example here, right, is if you had something like 0, 1, 1 reverse, then what do I do here? Well, I take the sort of the first symbol, so that's 1, I place it at the beginning, and then I reverse the rest of the string. So I do 0, 1 reverse, right? And just notice I'm using these parentheses here just to show that there's sort of like a difference here between sigma and then W reverse, right? So then I just apply this recursively, right? So I reapply this definition onto the smaller bit, right? So then I have 1, then I do the same thing. So in this case, if I have 0, 1 reverse, then I take this 1, I place it at the beginning, and I do the reverse on the remainder of the string. So I do 1, and then again, just for clarity, I'm going to use the brackets here in the parentheses, 0 reverse. Okay, and again, I'm not at my base case yet, right? So remember in recursion, you're always sort of, you're trying to get down to the base case, right? So you're sort of making the thing onto which you're doing the recursion smaller and smaller so that you can finally get to the recursive case, the base case, sorry, and then go back up, right? So here I'm not there yet because the base case is with the empty string. So I'm going to do this again. I'm going to say, well, Zero in this case, right? It might be a bit hard to see, but here it's as if I had epsilon was W, and then sigma was 0, right? So what I'm going to do is I'm going to take 0 here, place it in front, and then do the reverse here. So that's what I'm going to do. 1 concat with 1, and then let's see, 0 concat with the empty string reverse. Okay, hopefully I have the right number of brackets. And now this is when I'm going to sort of go back up through my sort of recursive calls. So here I have the empty string with the reverse applied to it, so I can finally stop and I sort of hit my base case. And so stop as in I don't have to do this anymore. I can just do my base case, right? So then I can sort of remove the brackets here and just have epsilon and then 0 and then 1 and then 1, right? Okay, so now 0 epsilon, right? If you take any string and you concatenate it with epsilon, then you get that string. So I'm just going to do that. So I'll have 1, 1, 0, and then a bunch of brackets. And then here, the brackets, I can start removing them because string concatenation is associative, right? So string concatenation is associative, meaning that if you have X and then Y, Z, so X concatenate with Y, Z, whole Y, Z, then it's the same as saying X concatenate with Y and then concatenate with Z, right? So it's like, it doesn't matter the order as long as it's like the sequence is the same. So meaning that it's X, then Y, then Z, right? But it doesn't matter the way that you sort of group them if they're contiguous. So with all that sort of description out of the way, then this just becomes 1, 1, 0, right? And then that's exactly what we had in the sort of intuitive definition here. So that's nice that that works out. Now, why do we need sort of the more formal definition? Typically, we need a more formal definition like this that has like a recursive case and a base case when we're going to do something that requires induction, right? Because then the point is that you can use the base and the recursive cases within the proof by induction, which is what we're going to do now. So now what we're going to do is we actually want to prove the statement. So we want to prove the following statement. That for every W and V in sigma star, W V reverse is V reverse W reverse, right? So maybe an example just to convince ourselves that this is true, right? If I have something like W is 1, 1 and V is 0, 1, right? And I want to compute WV reverse. Well, there's two ways. This is saying there's two ways that I could do this. Either I could do W and then concat V. So that would be 1, 1, 0, 1, and then take its reverse. So then skipping the sort of recursive column, just doing it directly, this would be 1, 0, 1, 1, right? So that's one way that I could do the string reversal when I have two strings concatenated. Or I could also do, this is what the statement is saying, V reverse, W reverse. So V reverse would be 1, 0, and W reverse, well, it's a palindrome, so it's still the same string. So it's 1, 1. And indeed, it looks like we had the same thing. Okay. And so this is kind of similar if you've taken a linear algebra course. This is kind of similar to the transpose, where you have A matrix multiplied with B transpose. Well, that's the same as B transpose A transpose. So it's the sort of same effect with the reversal, where you have to sort of swap and then apply the operation. Okay, so now how do we show that this is true? Well, in statements like these about strings and also about languages and also about like automata, it's often going to be the case that the easiest thing to do is some proof by induction. And then the induction is going to be on some like discrete property, of course. And it's often going to be a property of strings. One of the most common things to do in that case is to do the induction on the length of the string. So we're going to do this by proving it on the length of the string. So we're going to prove this. So do this. We will use induction on the length of the string. Now notice this statement in natural language is ambiguous because there are two strings here. So like which one is the string? Well, it's actually not that obvious until you see it. So there's quite a nice way to sort of re-represent this statement. So if I have the statement for every WV, WV reverse, V reverse, W reverse, what I can say is I can say that I want to show by induction. So really um, I want to use induction. Oh, what's going on there? I want to use induction to show that for some arbitrary, so notice this is a very important word, for an arbitrary string W in sigma star, for every V in sigma star, the property WV reverse is equal to V reverse, W reverse holds, right? So this might be obvious or not obvious, but basically what we're doing is we're saying, okay, we're going to prove this statement by induction, where we're sort of like fixing an arbitrary string W, and now we're going to show that this statement is true, this statement is true for every string V in sigma star. So now the induction on the length is naturally going to be on this thing, right? Because that's the string that has the for all, right? But then you might be saying, okay, well then that's nice, but then the induction is only showing that the statement is true for a particular W. But that's not true because I'm selecting W arbitrary. I'm saying that W, I don't know anything about it other than it's a string. So if I show that this statement is true by induction, then because I've selected W to be arbitrary, if I do this, then because W is arbitrary, then it must be that it's true for any string W in sigma star. Then the statement will hold. So then for any W in sigma star, in sigma star, the statement will hold. Okay, so this is maybe just a subtle thing and kind of like a review of your discrete math sort of proof technique. Or a proof technique that you might have seen in your discrete math class. Okay, so after all this talk, essentially what I'm saying that we're going to do is we're going to show this, right, by induction. Okay, so we're going to let W be some arbitrary string, and then we're going to show that the statement here is true for every string V in sigma star. Okay. So, how am I going to do this? Let me just give this thing a name. So show that for some. So let's say that this statement here, this is statement S, right? So we're going to show S by induction on the length of V. Okay, so how are we going to do this? Well, this is also going to act as like a review for your sort of induction proof technique. So how do we start the induction proof? We start with the base case, right? So the base case here has to be sort of the simplest possible string v based on its length, right? So in that case, it has to be the string with length 0, right? And the string with length 0, well, that's by definition the empty string, right? So now what we want to do is we want to show the statement S on the base case. So namely when V is the empty string, right? So we want to show that W V reverse is equal to V W reverse when V is the empty string. Okay, well, let's see. So I have W V reverse. Then let's just plug in V for the empty string. So I get W empty string reverse. Then we know that concatenating a string with the empty string is always that string. So I get W reverse. Okay. That's, oh, whoops, sorry. So I'm trying to show this. Okay. So that's not quite the statement here, right? But what I'm going to use again is that if I take a string and I concatenate it with epsilon from either side, it's still that string. So then this is still equal to epsilon W reverse. And then epsilon is the same as epsilon reverse. Why? Because of the base case in the recursive definition, right? So I'm going to use the base case in the recursive definition here. And I'm going to show, well, I'm just going to use it. So I'm going to say this is the same as epsilon reverse W reverse by the base case of the recursive definition. And then epsilon reverse, well, that's just V reverse by sort of plugging in, right? So this is actually V reverse, W reverse, and that shows exactly what I wanted to show here, of course, with the typo fixed. So hopefully you caught that even before I did. Okay, so that shows the base case. So hopefully that makes us happy. To make us even more happy, let's take the inductive hypothesis. So remember the second part of an induction proof. An induction proof is to state the inductive hypothesis. So we're going to say that we assume that the statement S holds for the length of V equal to N, where here N is greater or equal to 0, and is of course an integer. Okay. So notice I'm starting at 0 because that's where the base case started. And of course here N is for some arbitrary N. Arbitrary N. Okay, so that's the inductive hypothesis, second part of the proof by induction complete, but a short but very important part. Now the third part is the inductive step, where now we want to show that the statement S holds for the length of V equals N plus 1. Okay. Well, the length of V equaling N plus 1, we're going to use like a very common trick whenever you do a proof by induction on length of strings. And we're going to say, okay, the length of V is N plus 1. So that means that I can represent V in a certain way. And that certain way ought to be the way that it's represented in the recursive case here, because then I can use the recursive case that I've been talking, or that's talked about in the definition. So you kind of wanna imply sort of this implication wants to sort of be as a function. So as a function of what the recursive definition is. Okay. So in this case, the recursive definition is, you have W, or you have some string sigma, reverse, then that's sigma and then W reverse. Well, that's very convenient for us because now I can just say, well, suppose V, well, I mean, if the length of V is equal to n plus 1, then it means that I can represent V as the string U, concat sigma, where U is like V's prefix, right? So V's prefix of length n. So the length of U is n. And, sigma is just some symbol, right? Okay. So you're going to see very quickly why this is like kind of a useful thing to do. So what we want to show, of course, right, remember, is that for like this setting, right, where the length of V is n plus 1, we want to show that WV reverse is V reverse W reverse. Okay, so let's show this by starting with the left-hand side. So the left-hand side is WV reverse. Okay. At this point, I can't use I can't really use the inductive hypothesis because V is of length n plus 1, right? So I can't just immediately jump to that. Instead, the only really other thing that I can do is just set V to U sigma. So that's what I'm going to do. W is U sigma verse. Okay. Now, this still doesn't really help by plugging in. This still doesn't really help because this is still of length n plus 1. But what I can do is I can use the associativity of string concatenation where if I have W and then concat with U sigma, then it's the same as WU concat sigma. So you're going to see why this is kind of useful in a second. So I have this, right? So this is just by associativity. Associativity of string reversal. Then what I can do now is I can say, well, I have some string, right? I just have some string. I don't really know what it is. I don't really care. And then I have sigma, and then I have reverse. But notice that that's exactly the sort of thing the recursive case of string reversal is supposed to handle, right? You have some string, whatever it is, and then you have a symbol, whole reverse. Well, that's going to be sort of by definition of the recursive case, sigma and then W reverse. Okay, so then let's just use that definition. I'll take sigma, I'll put it in front, and then I'll do WU reverse. And this is by the recursive case of the string reversal. Okay, and now this is nice because notice U was the prefix of length n of V. So that means the length of U is V is the length of U is n, right? So if the length of U is equal to n, then I can use the inductive hypothesis, right? Because the statement S is, we fix this W, which is arbitrary, and now I'm assuming that the statement S holds for any string of length n, right? But U is a string of length n, so I can use the inductive hypothesis and use the statement S, which is namely that um, WU reverse is U reverse W reverse. So this is by the inductive hypothesis. And now the last thing that I need to do is maybe just um, convince the audience that this is V reverse W reverse. Well, if I sort of regroup again by associativity, I can get sigma and then U reverse, W reverse. And then sigma U reverse, well, again, by sort of the recursive case, this is equal to V reverse. This is equal to V reverse because, right, remember V is U sigma. So then if I reverse it, then I can use a recursive case and then get sigma U reverse, which is what I have here. So then it's fair game to replace it with this, right? Because, I mean, I have an equality. And so from the left-hand side, I get the right-hand side. And so that shows by induction. So then therefore, by induction, we have, we've shown the statement S, and then since W was arbitrary, since W was arbitrary, this implies that we have the result that for every W and V in sigma star, we have that W V reverse is equal to V reverse W reverse, which is what we wanted to begin with. So that's great. And so hopefully this is a good review on induction and also an interesting sort of use case of the string reversal.